Now we are actually going to the lecture notes, Appendix D. Or actually, we are looking at the book of Kallenberg. I think I prefer looking at Kallenberg's lemma 1.18 here in this case. There's a kind of concise treatment of consistency. What does this lemma say? This is a lemma that helps us actually eventually to work with linearity. So let's take any measurable function which is non-negative, and then we assume that f1, we have a sequence of functions. Now we get to approximation. So we assume that fn's are used to approximate f. So they converge pointwise to f. And these are simple functions. So they belong to this set simple, positive, all of these f1, f2, etc. And the claim is that then the limit of these simple integrals of fn, which are now, think about fn as, think about these fn's actually, maybe it's better to write this way. We have a sequence of fn's. Fn's belong to this simple space. They approximate f from below. We also know actually from section 3 that such functions always exist for every non-negative measurable function. This type of sequence exists, so think about approximating a function from below in this way. And then the claim is here that this limit, we know that these integrals by monotonicity, they also increase because the functions increase, the integrals increase as well. So the limit exists as an extended real number. And the claim is that this limit is bigger than the simple integral of g for all g which are dominated by f in this way. That's the lemma. And it does look a bit complicated, but let's see how we can work with this lemma. So let's look at the proof. I think it's helpful to understand kind of the deep detail of this, why things work. So case 1, we do a simpler case. We assume that G is actually an indicator of some set A for some set A, which is measurable, of course, in this setting. And we want to prove actually this claim, what we claim here. For now, in a special case where G is the indicator of A. Okay, this is of course a simple function, so it's part of the, and yeah, it assumes that G is less than F. So if this is our setting, so let's define another set AN as the set of points in A such that Fn is bigger than something. Okay, what is that something? We need to fix some epsilon as a helpful parameter. So let's fix epsilon in this part. And let's assume that Fn is bigger than 1 minus epsilon. And Fn evaluated at point S. Then what happens? Because Fn is pointwise increasing, so we get bigger and bigger functions when n grows. So for bigger function, this condition is easier to satisfy. So that's why these A's are increasing sets. So they increase when n grows. We get more and more points in this set. What is in the union? So they increase to the union of AN. What is the union of AN? Let's look. So the union, of course, belongs to A because all the points in every AN, these are subsets of A. So the union belongs to A as well. On the other hand, if we take a point from the set A, then what happens? Then we look at what's the value of Fs. It was dominating G, and G was G is equal to 1. So we conclude that F is at least 1 on this set A. And then we also know that we recall that F and S is increasing to Fs by this assumption about these Fn's. So the conclusion is that F and S must be bigger than, or at least 1 minus epsilon for large enough values of n. Yeah. So that means that S belongs to AN for large values of n. That means that S belongs to the union of AN. What did we do? We actually proved that if S is in A, so then S belongs to the union. That means that if we look at this here, so it was an inclusion, but actually it is a union. So it is equality. So this union is equal to A. That's important here. Namely, if you have a question now about this derivation, please ask. If not, I will clean it away. So the point was to prove that the union of AN is equal to A itself. What is the trick about this? We will prove the continuity of the measure. Now, you learned that the continuity of the measure mu that we have learned earlier translates to continuity of function approximation in a certain very special sense here. So what happens is that now AN sets are increasing to the set A, and that means that then by the continuity of the measure for monotone limits, so then the measure of AN also increases to the measures of A. Yeah. And what is the measure of A? Let's see. The measure of A is also equal to the integral of G. The conclusion now is that what we were studying are the integrals of these Fn functions. They are bigger than if we multiply the Fn by the indicator of something. So we multiply Fn by the indicator of An. That's a smaller function and still simple function. So then this inequality is true. And on the set An, Fn is at least 1 minus epsilon. So then this is bigger than the function where Fn is replaced by 1 minus epsilon times indicator An. By the linearity of the simple integral, we can bring 1 minus epsilon in front. So this is equal to 1 minus epsilon mu An. And now we know that mu An, this thing converges to the integral of G. So if we take limits from both sides, we conclude that the limit of this integral d mu is bigger than 1 minus epsilon, and then the limit here, which was the integral of G. And this is true for every epsilon, because epsilon was fixed here, remember? So this is true for all epsilon, what we proved. So it must be also true when we let epsilon approach 0. So we conclude that actually this is also true when we let epsilon approach 0, we get this one here. That's where we are now. So actually, what we did is that this claim is true when G happens to be an indicator of some measurable set. So the claim is okay. Or maybe if you have questions, so please ask now. No questions. So then let's clean this part away. Let's see how fast I can do it. So we have done this part 1, that the claim is true in the case G is the indicator of something. Let me open the claim. Okay, just cleaning here. And the lemma that we want to prove was found to be okay for G being a special thing, an indicator of a measurable set. The case 2 would be the general case where G is a general simple function dominated by f. So assume now that G is now a linear combination of 1 up to m ai indicator ai. Then there's a trick. Well, we assume also that all of these AIs are strictly positive, otherwise things get trivial. So in this case, then we note that if we divide by AI and we put indicator AI here and we multiply by this thing by F. So if you look at this thing, then because F was bigger than G, then we also know that this is positive. Indicator is a positive function. So then we get this type of inequality as well. And then if you look at what's the value of G in the set AI, so on this set, the value of G equals AI because we restrict with this indicator to the set AI where G happens to be AI. So what is there is actually AI times 1 over AI. This is just the indicator of AI. Okay. And then we apply the part 1. So by 1, we conclude that we also know that, okay, this indicator, and we multiply this by Fn, so these increase to the similar F, and then we can use the by part 1 to conclude that, what do we conclude? We conclude, we apply things to these functions that the limit n to infinity of the simple integrals of this case is bigger than the integral of this thing here, which was found to be this thing here, which is just the indicator of AI. So here we have, well, we can plug it this G d mu, and these are now these simple integrals still. So you see, it's a bit complicated, but bear with me, we're soon there. So what now? This is true for every I. So we sum over I from 1 to m. And actually what happens then is that, let's multiply everything by first this little ai. So then we can erase this denominator and we can erase this denominator there. Then we sum everything with respect to I from 1 to m. So we bring the sum inside the limit. It's a finite sum. We can bring the finite sum inside the limit. We are summing 1 to m here of these indicators, but that just gives us 1. So then we can erase this. The same sum happens to be there, the sum I from 1 to m. And then we look at this sum. These form a partition indicators, so these sum up to 1, so we can clean it up as well. 1 is there, hidden, and then we take it away. That's where we are. That's the claim, and we are done the general proof. So what was the general proof was this consistency lemma, so-called consistency lemma.